Okay, here we go. We're going to talk about precipitate reactions just briefly today, and then acid-base reactions, and just kind of see how far we can get. Just forgive me for any mistakes that I make while we're working on this, okay? All right. So you guys are pretty much acquainted with precipitate reactions. Here's our example. Two solutions are mixed in insoluble substance forms. You had some homework where you were trying to predict what the precipitate is, and I think those went pretty well. If you have any concerns, you can ask me. A couple of things I want to show you. I'm going to kind of go through this quickly here and find the slides I want to point out to you. Okay, these are just going through some examples. There's a nice, pretty yellow precipitate for you. And this talks about what that solid is and how you predict that. But what I wanted to look at was, here's your solubility rules. Not too difficult, I think. Just kind of group them into categories like they've done here for you. And the exceptions, you just have to work on knowing those. For the most part, the top half up here is going to be 1 through 4. Is going to be the ones that are soluble, and down here 5 and 6 are going to be your ones that are insoluble. So be careful when you're reading those examples so that you know what they're referring to. All right, and there's another nice white precipitate for you. So you can read through all of those, but I like this slide right here in particular, showing you on a particulate level what's happening when those solutions are mixed. So here we've got the potassium chloride in solution, and you see here what those particles would look like. They're separated, dissociated. Here we have silver nitrate. The thing I like here is it shows you that that nitrate polyatomic ion still is intact, that the N and the 3 O's do not break apart in solution, but that the silver ion and the negative ion are separate from each other. Then this particular circle here is showing you at like a snapshot of when these two solutions here are mixed together, and these are like at an instant, just all of those ions separated, and it's kind of a nice picture. And then at some point, which happens usually pretty quickly, the ion combinations that are not soluble come together, and in this case it'll be your chloride ion and your silver ion come together and aggregate here down at the bottom, and then you've got your nitrate ions and your potassium ions that are still dissociated. So actually what we've got here is we've got the potassium and the nitrate ions in this solution are actually our spectator ions. So if we were to look at the complete ionic and the net ionic, we would find those being our spectator ions. Okay, so I get used to this. Sorry, everybody. Then there's our equation down at the bottom. We're going to talk about the 3 different types of equations, and you'll have some homework practicing writing those. I do want to take a few minutes to talk about writing the 3 types of equations, just to make sure everybody's clear on that. This is continuing with some examples of predicting precipitates from solutions, so you can go ahead and read through those. All right, there's another couple of precipitates, and then this is talking about the different reactions that you'll have, the different equations that we can use to represent the reactions. So the first one is the formula equation. If you remember, I mentioned that those are also called molecular equations, and that's what I'll be using when I refer to those, okay? And then you've got an example there of a molecular equation. Make sure that they're balanced, and we have our states of matter there. Then we've got complete ionic. If you recall from first year chem, complete ionic is where we take the aqueous substances here, and they get split apart into their respective ions. So you have 3 substances here that are aqueous, and then the one that's the solid, which is your precipitate, remains together in its molecular form in this equation here. Then we have our net ionic equations, which is where we eliminate our spectator ions from each side of the equation there, and we write what remains, and that is going to be your precipitate and the ions that make up the precipitate. However, when we do write net ionic equations for acid and base reactions, you're not actually making a precipitate, it's water that's formed. So you would have hydrogen ions reacting with hydroxide ions to make water instead of seeing a precipitate, but you would still have a net ionic equation for that too. So there's an example of a net ionic equation. But I'd like to work one for you, if we can here. I want to get this pen in the right color. Excuse me, everybody. I like the yellow better. Okay, so here's our example. We have KOH plus FeNO3. Look at all those dots on the screen. And that reacts to form KNO3 plus FeOH3. Now, these two are aqueous. Okay. Khan Academy guy writes so much better than I do. And then we've got the aqueous over here, and we know that the iron hydroxide is a precipitate if you look at your soluble rules, so that should be an S there, pretty yucky looking S. So there's our formula equation or our molecular equation. The only thing we need to do yet is balance that. Okay, so we're going to need a 3 here in front of the KOH, and then a 3 here in front of the KNO3. So that's our completed molecular equation or formula equation. Now the next one we want to do is do our complete ionic. So that's where we look at our aqueous solution or aqueous solutions and breaking those apart into their respective ions, maintaining your balancing, and the charges are the charges are balanced as well. So up here we've got 3 potassium ions. We're going to put their little charge there, plus 3 hydroxide ions. Okay, it's a negative there. Plus 1 iron, and put its charge, and its charge we can determine, oops, I forgot my little 3 up there, by the equation here. Knowing the charge of nitrates -1, we have 1 iron, so it must be a +3 charge. And then we've got 3, that 3 on the outside of the parentheses tells us how many nitrates we have. So that's our reactant side of the equation. We'll put a little yield sign there. And then our product side, you again break apart your aqueous substance. So we've got 3 potassium, we have 3 nitrate, and then we do not break apart our precipitate. It remains intact because probably at the bottom of the container there we have all these iron ions and hydroxide ions that have aggregated and made that precipitate. And then we can put our little S there. Okay, so there is our complete ionic equation. Then to get our net ionic equation, we can look at our reactants to our products and cancel out anything that is similar, or actually it needs to be exactly the same. So that would be our potassium ions, and our nitrate ions are the same. And then we write what is remaining. So these didn't cancel, and neither did this. So here is our result, 3 hydroxides plus an iron ion, that's a plus, and then here's our precipitate. That's our solid. States of matter, probably in the complete ionic equation up here, I'm not so worried about the states of matter. Everything would be aqueous except for the precipitate. You must always show your state of matter with your precipitate. In the complete ionic, it wouldn't hurt if you put AQ, but I think it's kind of understood with them being in the ion form. But we must always, again, represent that precipitate. Okay? All right, so hopefully that helps with doing your molecular, your complete ionic, and your net ionic. Make sure you balance, and everything maintains its balancing. Okay, so I'm going to erase, so actually just clear that whole thing. All right, so we'll go on to the next slide here. Just get rid of this. Okay, I can't get rid of my silly eraser. All right. so there is our summary of the 3 types of equations. Okay, so then this gives us that example there. You can look over those and see how those are worked. I think I did example B for you is what I did. Okay. So next we're going to look at stoichiometry of reactions, precipitate reactions, and hopefully get into some acid-base reactions as well. So just as we've done before with our stoichiometry, you're going to have to maybe predict what the products are. You may have to determine what an excess reagent is, what a limiting reagent is, all those kind of things. The thing that'll be different with these reactions here is you'll be using molarity and volume to find your moles for your given reactants, whereas in the past we've usually been given grams that we're then converting to moles. So that's something else that we have to think about. We're kind of combining that molarity that we talked about earlier in the chapter now with our stoichiometry. There may be times when you have to find the limiting reagent, so remember you're going to do that when you are given the amounts of both reactants. Okay, and then you may have to determine an excess reagent. I think we've got an example of a problem where we're going to do that too. So sometimes it can be difficult to figure out what the reaction is, but for the most part I think you guys know how your precipitate reactions work and figuring out what your products are and that type of thing. And then remember that we are going to be using the molarity and the volume to be finding your moles for you to determine the result of your problem. Okay. All right, so here's an example. We want to calculate the mass of solid NaCl. It must be added to 1/2 liters of 0.1 molar silver nitrate solution. What we want to do with this is precipitate all of the silver ions that are found in the silver nitrate and turn it into silver chloride. So what the question is asking is how much sodium chloride are we needing to pull all of the silver ions out of the solution there. So we're going to do a little calculation here with that. So first thing is we're going to need a balanced equation for that. So I guess I wonder what my screen looks like on the next slide. Get it to move. Got a highlighter now. I don't want a highlighter or a laser pointer. Let's see if I've got a blank screen. There we go. Okay. All right, so our balanced equation, we have NaCl, and we're reacting that with, silver nitrate. So they're both aqueous. Okay, and then we're going to make sodium nitrate and silver chloride. Now, our precipitate here, if you go to your solubility rules, you'll find out that the AgCl is a precipitate, so NaNO3 is our aqueous here. And then given in the problem, they said we had 1.5 liters. Wow, you can't read that at all. That looks horrible. Go erase that. I try to write with my stylus, and I like writing with my finger better. All right, so we've got 1.5 liters of a 0.1 molar solution. That's a decimal point there, and that's a decimal point there. They are asking for how many grams of NaCl is required to completely remove all of the silver nitrate. Okay. Okay, so we basically have a stoichiometry problem. Not really any different than if we had massive silver nitrate wanting to convert to massive sodium chloride. But the thing is, we need moles. Remember, when in doubt, go to moles. So I'm going to take my 1.50 liters. I'm going to take my molarity as a conversion factor. And that's going to tell me how many moles of silver nitrate I've got. And that's 0.150 moles of AgNO3. Okay. Now, that would also be 0.1150 moles of silver ions, because we can look at this equation here, the silver nitrate here, and see that for every one of those formula units, we have one silver ion. So the number of moles of the silver ions equals the number of moles of the silver nitrate. So how that can help us is if we're using just the net ionic equation, we've got chloride plus the silver ion reacting to form silver chloride. Okay, so they react in a 1-to-1 ratio. Sometimes people like to use the net ionic equation to do their stoichiometry because you don't have to mess with the spectator ions, etc. But I guess I like to work with the formula equation or the molecular equation better, and then I can break it down into the respective ions if I need to. It's just I'm more comfortable with that. Other people may do things other ways. But so essentially we're going from the silver nitrate over to the silver chloride. Now that we have the moles of the silver nitrate, we see that we are 1-to-1 with the sodium chloride. So we have 0.15 moles of our silver nitrate. Sorry if I misspoke. Silver nitrate. Okay, we're going to multiply that by our 1-to-1 ratio, 1 mole of NaCl over 1 mole of silver nitrate. And that'll tell us the number of moles of sodium chloride that are needed. Okay, but we don't want moles, we want grams. So again, then we would finish that problem by taking the 0.15 moles of NaCl and convert that to grams by multiplying by the molar mass of silver or sodium chloride. So it would be 58.45 grams over 1 mole. When we calculate that, we get a 8.77 grams of NaCl that would be required. And then if you put, that means basically that when you add 8.77 grams of NaCl to the silver nitrate solution given, all of those silver ions will come out of the solution, bond with the chloride ions, and make this precipitate here, the silver chloride. And then we'll have spectating, we'll have sodium ions spectating, we'll have nitrate ions spectating, all right? And then that'll be it. So I hope that problem makes sense to you. I guess one thing to keep in mind is if we had a situation where we were not at a 1-to-1 ratio like we are here in this net ionic equation. I'm going to clear this screen here and try and show you just briefly what we would do in case we weren't at this 1-to-1 ratio that we see here. So let's see if I can do this without making too much of a mess. Okay. All right, so now we're going to pretend land. So let's say we have two, oh gosh. Okay. I didn't select the correct thing, did I? I want the pen. There we go. Let's say I have 2 chloride ions for every 1 silver ion. And that means this is not true, but I'm just trying to give an example of how this problem would change if we had a 2-to-1 ratio instead of 1-to-1 ratio. Okay, so we said earlier that if we had 0.15 moles of silver ions, then before we needed 0.15 moles of chloride ions to react with that because we were 1-to-1. But here we are at a 2-to-1 ratio. So if I have 0.15 moles of silver ions, the amount of chloride ions needed, basing that on our mole ratio, would be twice that, because our silver ions would go on the bottom, our 2 moles of chloride ions would go on the top. Okay, and then that means we would actually need 0.3 moles of the chloride ions to completely pull all the silver out of the solution to the precipitate. And then you could further take that, knowing that NaCl is a 1-to-1 ratio, so that means you would also need 0.3 moles of NaCl, and then you can further convert that into the grams by multiplying by the molar mass of the NaCl. All right, so that's an example of what you would do if you weren't at a 1-to-1 ratio. Just always make sure you're checking on those mole ratios when you are doing any type of stoichiometry. Okay. All right, so let's clear that screen and we'll go on. So here, further on in your slideshow, they go through this. I just kind of did it all on that one slide for you. So you can go through and read that if you didn't understand what that guy was saying. All right, so this is a summary of the different types of steps that are involved in stoichiometry problems with solutions. So it's really good to go through and read all of these steps. So we've got identify the species present. So you're basically finding out what the reaction is. Then a lot of people, like I said, like to use the net ionic equation for this. It just eliminates the spectator ions. Again, I prefer to work with the molecular equation. You calculate the moles like we've done before, but the thing that's different with reactions in solution is a lot of times you're given molarity and concentration. And then you may have to determine the limiting reagent. You may not. Remember, you determine the limiting reagent when you're given the amounts of 2 reactants. And then you calculate the moles of products and then convert that to whatever unit that you need for that. Okay. All right, so let's see. Here's an example. We're going to look at that. This precipitate reaction. Okay, so we have sodium sulfate and lead nitrate. They're mixed together, and we're making, sodium sulfate and lead nitrate mixed together, and it makes lead sulfate. We're going to calculate the mass of the lead sulfate formed, and it tells us the amounts of lead nitrate and the amounts of sodium sulfate that are mixed. So again, it's really important to write your balanced equation, and then I strongly emphasize that you label the things in your equation. So let me get the right slide here for you so I can do that. Again, lots of writing here. Okay, so here's our equation. We had Na2SO4, that was AQ, plus PbNO3. I'm sorry, you guys, my writing is really horrible on this thing. And then we make 2 sodium nitrates plus lead sulfate. Okay, we said our sodium sulfate was aqueous and our lead nitrate was also aqueous. They were both solutions. So we look at our products and we figure out what would be our solution and what would be our precipitate. And if you look at your solubility rules, you'll find out that the lead sulfate is our precipitate and the sodium nitrate is our is aqueous, dissolved there. Okay. All right, so I've got 2 liters of this sodium sulfate, and the molarity is 0.0250 molar. This was all given on the other slide. I just moved to a blank slide so I could write this out. Terribly messy for you, looks like. And then we have, for our lead nitrate, this guy here, okay, we have 1.25 liters of that. We have a 0.0500 molar concentration of that. So these are what we're going to use to find our moles. Now notice we have the amounts of both reactants. That means we're going to have to find our limiting reagent. So I'm going to start by converting my volume of both of them into moles. And I'm going to use my volume and use my molarity, 0.0250 moles for every 1 liter, and that gives me 0.0500 moles of Na2SO4, sodium sulfate. And then we'll do the same thing with our lead nitrate. So we have 1.25 liters, and it's a 0.0500 molar over 1 liter, and that gives us 0.06250 moles, and that's our lead nitrate. Now what we're trying to do here is figure out what our limiting reagent is, so that we can then predict how much lead sulfate is formed, because that is what we were looking for, is the mass of the lead sulfate. All right, so it looks like, looking at our equation up here, our coefficients are 1 in front of the sodium sulfate, 1 in front of the lead nitrate, and that means that we're at 1-to-1 ratio. So this is an easy choice as to what's our limiting reagent. We simply look at these two numbers here, and we're going to pick the smaller of the two, and that will be this guy right there, and we'll have sodium sulfate as our limiting reagent. So then the rest of it looks very much like what we've done before, ad nauseum, you probably think. Converting our moles of sodium sulfate. Using our mole ratio, it's 1-to-1. 1 mole of lead sulfate. Got 4 in there. To 1 mole of Na2SO4. And then we're going to do one last step where we're going to convert that to the mass. And the mass of lead sulfate is 303.3 grams for every 1 mole. Okay. And then that will give us 15.2 grams of lead sulfate is how much is formed with those two solutions when they're mixed together. Again, we would have spectator ions present. We would have sodium ion spectating. We would have nitrate ion spectating, and we know that because of the fact that the lead and the sulfate are the only ions that made the solution, or made the precipitate. So the sodium and the nitrate weren't involved in the reaction at all. We can also do more complex things where we can then find out, well, based on our limiting reagent, which of these two ions, the lead or the sulfate, are in excess in our solution. Okay, and we know here by looking at the fact that this here is our limiting reagent, that means that all of the sulfate here is consumed and turned into the lead sulfate, but we're going to have some extra lead left over in the solution. So that would be another type of problem that we could do, is figure out, based on our excess reagent, what the concentration of the ions and etc. are left in solution. I think we have an acid-base problem where we're going to do that. Okay. All right, so let me wipe that board clean and we'll move on. Okay, so again, this goes through all those steps. So if you couldn't read my chicken scratch, you can take a look at that and follow. And again, this one is actually worked using the net ionic equation, so if you want to see an example of how that works, a great way to see how that works. Alrighty. So now I think we're ready to talk about acid-base reactions, and we've got just a couple examples here of that, and then we should be ready to give you your homework. Looks like I'm about 28 minutes in here. So, all right, so let's talk about acid-base reactions. So there's 3 different definitions of acids. The first one is the Arrhenius acid and base definition, which is probably the most straightforward, the easiest one to recognize. However, it's the most limiting. It really limits which compounds can be classified as an acid or a base. So according to Arrhenius, remember he's the one that was working with the electrolytes, an acid is a substance that produces hydrogen ions when it's in water. Okay. It won't, if it's just a solid, it isn't behaving as an acid. You need to have it in a solution in order for that substance to actually behave as an acid. And then a base is a substance that produces hydroxide ions. So it's a real easy way to recognize an acid and a base. But then again, you're limited to substances that have hydroxide in them in order for them to be a base, and not all substances that are basic have hydroxide in them. So more general and more broad definition is the Bronsted-Lowry concept of acids and bases, and that's it's probably the most common way that we talk about acids and bases. And an acid is a proton donor, okay, and the base is a proton acceptor. So that opens it up a little bit. Notice the base definition, you do not have to have a hydroxide in it. You just have to be the substance that actually is accepting that proton. Again, we're going to talk about acids more at the end of the year, and we'll see all of this arise again. But now we're really looking more at the stoichiometry that's involved with this in this chapter. Okay. We talked about strong acids and strong bases, and weak acids and weak bases. Strong acids, if you take a strong acid and react it with a strong base, here's our example. We've got HCl present here, and then we've got NaOH there. Those are the strong acid and then our strong base. When they react, they're going to make water. Okay, and what we've got here is the net ionic equation. So if you wrote the molecular equation, you'd have HCl plus NaOH making H2O, and then you would have sodium chloride as the other product. But then when you remove those spectator ions, and in this case the chlorine and the sodium are going to be the spectator ions, and all you've got is the hydrogen ion plus the hydroxide ion yields the water. Okay. And when you have a strong acid and a strong base reacting, when that salt is formed, that salt is always considered soluble. Okay, it'll always be a soluble salt as long as it's a strong acid reacting with a strong base. Okay, if you have a weak acid with a strong base or vice versa, then the salt is not necessarily going to be soluble. It may be, but it isn't always. Okay, so here we've got a weak acid and a strong base. When they react together, this strong base here is strong enough to actually pull the hydrogen away from this weak acid, and we'll see an example of that in a minute. But here we've got our acetic acid and then lithium hydroxide. We know lithium hydroxide is a strong base because it's one of the ones that we have to memorize. Remember, that's how you know if it's a strong acid or a strong base, is by memorizing those. So here is our net ionic equation of a weak acid and a strong base. What is spectating here is the lithium ion, and that is what you do not see over here. If we did the molecular equation, we'd have LiOH written over there, and then on this side, on the product side, we'd have LiC2H3O2, but it's a spectator. Okay, so that is not represented then in our net ionic equation. So we have the hydroxide from the lithium hydroxide reacting with the acetic acid. Now you may notice here that the acetic acid is written in its molecular form. It's not written in its ionic form in this net ionic equation because it's weak, which means it does not completely dissociate. So most of the molecules of the acetic acid that you placed in the water are still in their molecular bonded form. So in our net ionic equation, we represent that by keeping it in its molecular form. So any weak acid or weak base that you would have in a net ionic equation on the reactant side must always be in its molecular form. Then what happens is this hydroxide here is strong enough to rip this hydrogen away from that weak acid, and that hydrogen and that hydroxide bond and they form water. And then what remains is this C2H3O2, the acetate ion, which will not bond with the lithium because lithium is a soluble ion, so it is not going to bond with the acetate. So we would have both of those ions kind of floating around in there, and our product is water. Okay, so this time we do not have a precipitate formed, we have water formed. Okay, so that looks a little bit different on my scribbles again. Okay, and again it mentions the lithium. Okay, so that's an example of a type of reaction with a weak acid and a strong base. All right, so calculations with acids and bases similar to our precipitate reactions in solution. All right, make sure you determine what the reaction is by looking at the reactants and predicting what the products are. That's where our double replacement reaction knowledge comes into play. You can write the net ionic equation if you like for that. Sometimes it's helpful. Sometimes you may want to go with the molecular equation. Then you need moles in order for you to go from one substance to the other. You most likely are going to be using the volumes of the solution and their molarities to determine that. Make sure you do your limiting reagent. If necessary, convert to the moles of the product or reactant in question. If we're doing an excess reagent problem, remember we would go from the excess reagent to, or I'm sorry, from the limiting reagent to the excess reagent to look for any ions that might be left over that haven't been used. And then maybe go to grams in the end, or volume if you needed to know what that was. Sometimes we might even in the end go to a molarity, find the concentration of what's left over. I think we have an example of that. Okay. All right. Now this definition here is helpful. This tells you what neutralization is, and neutralization is when the acid and base react in just the right proportions so that there's not an excess, basically, okay? All of the acid and base have completely reacted with each other. There's nothing excess, and so you've basically just made water. You have nothing left over that might cause the reaction to have more hydrogen ion, hydroxide ions, which would make it acidic or basic. That means you have neutralized the solution, and we're going to do some titrations later on in probably this coming week where you're going to work on neutralizing a solution. Okay, so let's take a look at this example. We have a volume. What is the volume of 0.1 molar HCl that is needed to neutralize, so completely react? So we want to know what exactly amount of HCl we would need to consume the 25 milliliters of a 0.35 molar NaOH solution. So equation is what you're going to need to go about this problem. So I'll try it on this side. HCl, which is going to be aqueous, and we're reacting that with our NaOH. And according to our double replacement concept here, okay, the Cl and the OH switch places. So we're going to combine the NaCl, and that will be our soluble salt. Okay, and then the H plus and the OH come together, but we don't write them as HOH. We always write that as water. Even though it's coming from an ion here and an ion here, God does weird things, okay? He takes those two together and he makes something molecular out of that. So we will put an L behind that to show that that's a liquid. Okay, and then our salt is soluble. All right, so let me see if I can get rid of this up there so I can label. Okay, so we have 25 milliliters of the sodium hydroxide, and the concentration is 0.35 molar. And we are going to use a 0.1 molar solution of HCl to do that, but we want to know what volume of this HCl solution is needed to completely use up all of those hydroxide ions and turn that into water. We don't want to have any ions of the hydrogen or the hydroxide left over. We want them to react completely. So our net ionic equation is H plus OH minus yields H2O. Okay, so I'm going to, I don't think I can continue. Let me see if I can get rid of some of this mess in there. Good. So, all right. So really what I need to know is how many moles of NaOH I have, so that I can then figure out how many moles of HCl are needed. And then I can use my molarity to convert from moles to volume. Okay, so let's see how that's going to work. So I'm going to take my volume of my NaOH, I'm going to convert that into liters because I'm going to use my molarity to convert that into moles. So here's my molarity, using it as a conversion factor. It's nice if you guys can get used to doing that. All right, and that's going to give me, oh shoot, I didn't do it that way. Let me just figure out what that is real quick. All right, so that gives me 0.00875 moles of NaOH. That means I need, because these react in a 1-to-1 ratio, I need that amount of moles of HCl to completely use up all that NaOH since they react 1-to-1. So then I need to know the volume of this HCl solution here. Oops, what did I just do? Okay, I need the volume of this guy here. I know the number of moles that are needed. I know the concentration is 0.1 molar, but I want the volume. So this time I'm going to take my molarity and I'm going to put the moles in the bottom and the 1 liter on the top. And that's going to tell me what is the volume of HCl that would need to react with that. And that ends up being 0.00875 liters, which is also 8 point, oh, I did that wrong. Sorry, guys. Go back here. I should erase that. 0.0875. So that means I'm going to need 87.5 milliliters of the HCl to completely react with the sodium hydroxide, and then it'll make water. So that's called a neutralization reaction. Now, if you weren't at a 1-to-1 ratio like we are here, okay, then when you were doing this step here, let me get rid of, again, some of this stuff here. Okay. If I weren't at a 1-to-1 ratio, let's say this were a 2 up here, I should change colors. Let's say this were a 2 up there. Okay. Then I would take my 0.00875 moles of NaOH, and then I'd use my mole ratio, 2 moles of HCl over 1 mole of NaOH. Okay, and so I'm basically doubling that. I would need 0.0175 moles of HCl. And then I could continue on with my molarity, find out what volume that would be equivalent to. So you do have to keep in mind on your mole ratios when you're working with these problems. Okay, so your book a lot of times chooses 1-to-1 ratios, and then in your problems at the end, they end up throwing you a 2-to-1 or 3-to-4 ratio or what have you. So keep that in mind. All right, so I hope that makes sense to you. Again, going on, goes through all of this stuff that I just did with you on this slide. Okay, so here we've got another example. Let's see what we've got here. Take a look at my time. Okay. Maybe I should stop here at this point. You guys are sick of hearing my voice anyway, and that's probably enough. So let me modify the equation, the problems I'm going to give you, and then we'll pick up with this on Tuesday. So I hope that this wasn't too annoying for you to do and listen to me. So have a great weekend, everybody. And what I'll do is I'll post the homework problems that you're to do that pertain to this lecture on Canvas on the calendar. And so you'll know what ones you need to do for Tuesday when you come to class so we can go over them in class. Okay? All right. Good luck, everybody. Have a great weekend. We'll see you later.